Andy, thanks for taking some time with me today. I've been kind of jumping all over the building, spent some time with Pierre really talking about what goes into our design and aesthetics and, you know, ergonomics of our products. Mike was kind enough to show me acoustically why we sound so good, but, you know, of course, those things are still only part of the puzzle, right? At the end of the day, we've got to make sure that our products are reliable and they're safe, and was hoping you could tell me a little bit about our processes that really ensure that we're strong there too.
Sure. Well, it's a big part of loudspeaker design is to make sure that your product is reliable, and it's absolutely crucial that it's 100% safe.
Yeah.
Yeah. So the one demonstration I've got for you here is how we do our pull testing.
Yeah.
Okay, and this is to ensure when we hang loudspeakers, especially if it's above people's heads, that we design to the right safety factor, which means that we can ensure that, you know, no one's ever going to get hurt or any equipment's going to get damaged or anything like that. Typically, we'll recommend an 8-to-1 safety factor for overhead stuff, which is in line with most of the modern standards, DGUV, ANSI, ISO, these kind of things. But normally when we have the line arrays, for example, we have software selectable. You can select 12-to-1 or less as well, depending on the local regulations or the type of installation. If it's not overhead, then maybe you don't need such a high safety factor.
Okay, so if I understand that safety rating 8-to-1, if a speaker weighed 100 pounds, it would have to hold 800 pounds?
Sure, absolutely. So if a speaker weighs 100 pounds, then the rigging and everything that holds it up has to be able to withstand 800 pounds before it breaks. So that means you have this really large safety margin in between what you're actually doing and what this structure is capable of holding.
Well, I mean, it's an impressive workshop. What is this medieval device, and what do you do with that?
Well, this is a pull tester, and it's a load test machine. What we do is we pull vertically on components or even full loudspeaker systems to determine the yield strength of the material, and then also the break point of the material.
So you basically just attach whatever it is right here. You've got something in there and you pull until it breaks, right?
Absolutely. I've got an example here. The one that we're going to do, this component is the same as the one that's in there. This is a spreader bar, and this holds the whole weight of the line array.
Wow.
And from this single pick point here, you will end up with 840 pounds underneath it.
Wow.
So we have to ensure that this is able to do 8 times that amount. So that's nearly 7,000 pounds.
Wow.
From that single point.
And this is steel, aluminum? What
that's an aluminum extrusion, and it's a special hardened type of aluminum.
Wow. And so this is capable of so much more than just, you know, a few boxes. And the reason for that is, why is that safety factor so high? Is it because if something breaks, now that load has shifted? Or?
Well, if you had a one-time safety factor and then you lifted it, then it would break.
Sure.
Because you're putting a dynamic load onto it. So dynamic loads are typically 2 times, and you want a safety factor over that, which is maybe 4 times. Total safety factor. And then when you start looking at stage handling spaces and overhead, then most of the standards like DGUV and ANSI and these kind of things, they will recommend that you double that again. So that's where you get the 8 times from.
Okay, so more than safe enough. And that's obviously very important. I mean, I recall seeing, I think in the last few years, several stages with wind and stage collapses, and you know, I remember seeing where the truss actually came down, but the speaker systems were still hanging in place. Well, thankfully, it wasn't one of our systems twisting in the wind there, but you know, it goes to show how important safety can be. Absolutely,
and we make sure that our designs are to the standard that will never happen. Okay, so this is an XLE line array box, and on top of it, we've got the grid. So this consists of 3 parts. We've got the side arms, we've got the spreader bar, and then this is a shackle, and this would be where you would lift the line array up with a single point hang. So you'd hang the whole line array off this single point.
And you can do single or dual point, or even 3, I guess.
Well, usually you'd use this for safety.
Okay.
And then if you do a dual point, you'd have 2 spreader bars, and you pick it up at the front and the back, and that allows you to angle it.
Okay, makes sense.
Yep.
And then that can hold up to how many boxes?
This one's designed for up to 16 boxes.
Okay.
We've got line array prediction software, which actually may allow you to do a little bit more, but as the standard calculation is 16 boxes. And that 16 boxes will go up with the XLD, will go up to about 840 pounds.
Oh, wow.
Yeah.
And that's because each box weighs approximately what,
The XLD is about 43
43
pounds
pounds.
each.
So relatively lightweight for a line array box, really. I can only imagine that economies of scale, as you get bigger and bigger, you must be dealing with some hardware that, can be in excess of 10,000, 20,000 pounds. Right?
Absolutely, and one of the major design goals with a line array loudspeaker is to make it as light as possible, because the heavier the box gets, you multiply that by 16, suddenly you've got a lot of weight. Then your rigging has to get bigger and stronger, which then gets heavier, and you end up running away by the scale of the whole system.
And of course, at the end of the night,
wasteful.
some poor guy has to load it all into a truck and move it somewhere.
Absolutely,
So.
and then you've got a limit on the pick points in the ceiling of the theatre or wherever you're hanging it in a festival, perhaps. And you may have a half-ton limit or a 1-ton limit, maybe even a 2-ton limit. So you have to work within all of these limits. And we're factoring in all of these things when we're making the designs.
And that safety is not only in the bigger parts of the rigging hardware here, but even the pins and the bars inside, right, also have to be tested, right?
That's right. And as you see, the way we design this box, it's actually a wooden box because it's very high strength and it's great for the acoustics. But all of the structure goes through the steel or aluminum parts.
Okay.
So when we're calculating the structural parts, you're always calculating steel to aluminum to steel to aluminum, and then things like the quick release pins are a special kind of hardened stainless steel. So every single component has to be individually tested, and then we test the system as a whole.
So obviously, yeah, because no system, when you're hanging it has to be at least at its weakest point and beyond that. So testing every part, certainly makes sense. So this bar here is really the linchpin, and everything else goes along with it. Okay, tell me how this thing works exactly now. Obviously, it looks a little dangerous.
Okay, yeah, well, safety first. Well, let's get some goggles on.
Thank you.
When we do the actual test, we'll make sure that everyone's behind a very strong plexiglass screen as well. We don't expect anything dangerous to happen, okay,
Sure.
but we do always think of safety first. So I'll just explain the machinery and I'll explain how it's safe and all that kind of stuff. This is a device under test. This is the XLD spreader bar that we saw before. We're going to pull upwards from this point here with this very large mechanical pull tester. This will take up to 10 US tons.
Okay,
Okay,
wow.
so this is a big one.
20,000 pound.
This thing here is called a load cell, okay, and that measures the number of pounds or kilograms force that's coming up this way, and that displays it on this little display over here. Okay, so we can monitor that as we're pulling it. The way the test is set up, we've then got these two rigging pins into two jigs here attached to ground. So you'll get this force divided by 2 at each end.
Okay.
Okay. So what we're testing, is it strong enough at this point here? Mm-hmm. Is the fundamental bar strong enough, and are the pins in the end strong enough as well?
So the stress point is here,
Yeah.
and then basically shared. So
here and here.
If this would be 10,000 pounds of force, this would be shared 5,000 pounds each?
Each, yeah, absolutely.
Okay. So in all likelihood, I mean, I guess the reason you test is to try to figure out, where the weakest points are and to improve upon them, right?
Well, what we want to achieve with this one is 6,800 pounds, because that will give us 8-to-1 with a 16-box hang.
Okay, got it.
Now, we won't stop there. We'll carry on to destruction. I don't know how many pounds we're going to get out of it with destruction, but
That's my favorite phrase I've heard all day. Carry on until destruction.
Absolutely.
That's the best.
So we might get 10-to-1, we might get 16-to-1, we don't know. And then once we find the break point, we can calculate backwards from that, saying, well, you can have 16 boxes with an 8-to-1, you can have 8 boxes with a 16-to-1. So it's all relative.
Okay, got it. Okay, so we figure out where it is, and as long as that's falling within what we need, we're good to go.
Basically, we break it and we specify it, so no one will ever break it again.
Do you have to go through this process multiple times to make sure that the results are consistent?
So, well, it depends on the exact thing. If you've got a line array box that can be rigged at multiple angles, you will actually test it at a number of different angles, and you will find out a stress curve throughout all those different angles.
Because that varies.
Because it varies depending on the angle. With a part like this, we might test an original early prototype part, and then when we actually get to production parts, we would then test the production parts. And if we ever changed for example, the aluminum supplier or something like that, then we would test the parts again to make sure that the final parts are still performing the way as the original design intent.
Always making sure it's up to the original specified
Absolutely.
plan.
So we design it to a certain load factor, and then we verify it to that load factor throughout the manufacturing process as well. Okay, so now we're getting ready to do the test. We're going to pull up from here, and the last thing to do is to make sure that everything's properly secured. We have to make sure that the load ratings of all the connecting parts are much higher than the actual test itself. And then you might have noticed these yellow straps that are everywhere. These aren't part of the test, they're all slightly loose. And these are all, just in case something breaks, we're trying to think of where all the parts will go. Is this going to swing out? Well, it's protected by this. Is this going to fly out this way? It's protected by this. So you can kind of ignore these parts for the test. The only thing we're really concentrating is the force here in this vertical section and the two forces at the side. We're expecting the thing to bend up like this somehow, and we're flexing this really strong T-shaped piece of aluminum, so it's going to take quite a lot of force to do that. And then we're looking for potential failures at the pins at the end and at the center part here. Okay. Okay, that's about 840 pounds, which is the weight of 16-box line array. We now have to go to 8 times that, so nearly 7,000 pounds. That's 6,800 pounds. So that's 8 to 1 safety factor, 16-box array we've passed. Now let's go on until the break point. 8,000, 9,000 pounds. You can see severe deflection of the beam. So the beam's now yielding because as I put more force on, it's not holding it easily.
Ooh.
And that's structural failure.
Wow. It didn't sound like I thought it would.
Pretty close to
but
10K.
Wow. So 10,000 pounds almost out of that little chunk of aluminum. I mean, I trust you guys to hang speakers over my head anytime. Can we just take a look at where it broke?
Absolutely. Let's get this off. Yeah,
right there.
Absolutely.
I mean, I guess it broke where you expected it to.
Yeah.
But the interesting to me, I expected a much larger boom when it went. It was kind of this low thud. I mean, do you get different results every time it goes? I mean,
It depends what material you've got. If you've got hardened steel, for instance, it'll crack quite strongly.
Okay.
If you've got stainless steel, that tends to bend a lot. You get a lot of yield before it actually does the ultimate failure. And this is for the X12-125F flying subwoofer. So that has to take a much stronger weight, and that's up at 18,000 pounds, which is pretty close to actually the maximum we can do on this location with our manual rig.
Well, yeah. I mean, you can see that nearly twice the amount of material and twice the amount of weight that this one held. Is that fairly consistent with the amount of material that you see that's linear?
Well,
or?
Yeah, well, I mean, you can calculate it, and really for this particular structural break, it depends on the thickness of the material that you've got from the side of the hole.
Okay.
As you can see, it's broken here. And then the overall strength, it depends on the T-section as well.
Okay.
And then it gets more complicated when you've got a pin in a slot, for example.
So stupid question for me then, why wouldn't we just move that hole closer to the bottom of that bar?
Because you'd never fit your shackle through it.
Okay.
So we've designed it to the exact limit that we wanted to, but we haven't over-designed it because that would be introducing more cost into the project.
Well, that makes sense. I mean, thank you for showing me this. I mean, like I said, I trust you guys to hang speakers over my head. So when we're making speakers, we got to do it safely. We've got to make sound. We've got to make good sound. But we also have to keep making sound, right? We don't want our speakers to stop working. So that's another area entirely that you guys work in, right?
Yeah, absolutely. As you can see, this is mainly about safety.
Right.
So we're testing its safety. We also need reliability, and these speakers need to last 5 years, 10 years out in the field without any maintenance, preferably. So we have a lot of challenges, especially with the transducers and the crossovers. These are very sensitive components, and we have to run them up to high temperatures.
Would you show me that too?
Absolutely.
We're outside the famous EV power test room. I hear this room when I pull up to the office and park my car in the parking lot. I get out and I can hear the faint thump, and obviously can hear it. You know, we're standing outside is there 2 or 3 rooms in here, or?
Yeah, so the power test room has got 3 levels of isolation.
Okay.
So it's got an inner room which is all brick, and then it's got a secondary room which is all brick, and then it's got this third room. So it's triple insulated against the noise. We have a power test running at the moment. It's not a really full level power test. It does get louder than that, but as you can hear, it's quite okay out here.
Yeah, we're taking it easy just so we can hear each other talk here. But yeah, I've heard it at times where it's in the parking lot. It's significant. So I mean, I know what you guys are doing in there, but tell me a little bit about what you're testing for and what that process looks like and
okay,
how that
at the
works.
moment, we've got 3 different tests going, basically. We have a system test, and that's a thermal test. So that's just noise you can hear in the background, a kind of low pink, modified pink noise.
And the system, you mean a full
loudspeaker,
okay.
woofers, tweeters,
Got it.
crossover. And at the same time, we're doing a transducer test for low frequencies with an AES style test, which is also a pink noise. We're doing a low frequency woofer test that we call a bump test, which is proprietary to Electro-Voice, and that tests maximum excursion and the ability for the cone and the loudspeaker components to withstand, the maximum
Really
force that gets
thrown
put
out.
into them.
And that's, I assume, the thump we're hearing right now.
That's the thump, absolutely. And then we've got a high frequency test, which is an AES pink noise test as well for compression drivers going all at the same time.
So we're using both industry standard tests as well as doing our own unique things.
Yeah, we use the industry standard test, and then we go above and beyond that. And we push everything to the limit, just as we do with the pull test for strength. We want to test the loudspeakers absolutely to the limits so that we know where they are, and then the users will use those slightly below the limit so that we know that it can last a very long time.
Cool. Can you show me?
Yeah, absolutely. The thing is that before we get anywhere near it, we need some hearing protection.
Let's
put on a first level
we came prepared. I'm ready.
It's not too loud in there at the moment. So.
Okay, well, better safe than sorry, right? So.
Okay, so this is the control room for the power test, past the first door. And up here you see a large amplifier rack. This has got 250,000 watts of amplifiers in it. That's half a megawatt of amplification.
That's a lot.
We don't normally use all the channels at the same time. It means we can run different tests at different times, all that kind of stuff. This one amplifier here, that's a 20 kilowatt amplifier. And you can hear the test going on in the chamber. So depending on the test, depending on what we want to measure, what we want to track and record while the test is going on, this is logging temperature on several different devices inside the system test at the moment. And you can see that some of the components are getting quite hot, but we take them up to a certain temperature, and then we push everything to the limit and then keep it there. We've got a control computer in here that produces all of the different signals through up to, I think it's about 30 channels output on that. And we can measure peak voltage and look at the waveform on an oscilloscope. And we've also got a high accuracy voltmeter there to record the levels. All of the signals are patched in and out of the chamber. These are the loudspeaker patches. So each one of these connects into the chamber through a soundproof connection so that the sound can't get out at the same time. So we can look at any of the voltage levels on any of those connections while the power test is going on in there and control everything.
So you're actually monitoring from here as well. You're running the test and monitoring it all in one space.
Absolutely.
Okay. All right, so where are we going now?
So this is where we go through the second level of protection. So this is now a solid brick wall. Okay, and as we go in through here, we have to put additional hearing protection on. So we've already got the...
It's getting louder,
let's get
right?
the fenders on.
Oh, wow.
So now you can hear the...
Yeah, you start to really feel the...
I don't know if you can still hear me, but this is what the third one's like.
Okay, kill it! So now that we've shut off whatever it was you were doing in here, just so we could hear ourselves think, unbelievable how loud it was. And you said that wasn't even really getting on it, right? You had a lot more.
Yeah, some of these are 10 dB below maximum, and the main system test was 20 odd dB below maximum.
I can't even imagine.
So it's really, you can't come in here when it's at absolute maximum.
Yeah, that's just crazy. So, but you're doing all these different tests, and I come in this room and I smell, burnt stuff. I see burn marks on the floor. I mean, you can tell you guys are really putting the screws to this stuff and making sure we know, where they break and then improving upon that, right?
Absolutely. So, I mean, there's kind of two sides to it. One side is to develop things for R&D. So you want to take it to destruction, find which parts fail, and improve those parts, and then you keep improving it so that the whole system gets better in a balanced way.
Right.
And then the second side of it is once you've done all that designing and you've got your kind of, pre-production parts or something, you'll bring the speaker in here and you'll run a long test that will then validate that all of the production parts are still
working
performing
together
the way that you expect them to compared to the R&D design originally.
Okay, so once that's done and you've got a system that you say is reliable, I mean, where is that line drawn? I mean, what's our minimum when we make a system, a speaker enclosure?
Okay.
Our low bar is what?
Well, you can break the test down into two kinds of tests, really, fundamentally. We do a number of different tests, but you've got thermal.
Okay.
And then you've got kind of peak, excursion, and long-term reliability.
So thermal, you mean literally gets so hot and does it catch fire and burn
Absolutely.
up?
So
right?
typically with a ceramic magnet like this, the actual magnet may be at 100 degrees centigrade.
Okay.
And the voice coil inside could be 200 or 250 even degrees centigrade.
So literally
these things
burning.
Get very hot. So we'll test and we'll take them to equilibrium, and there's different standards. Some people do a 2-hour test, we do an 8-hour test to make sure that it can withstand that thermal load for that length of time. If it withstands it for that length of time, it should carry on. Then we do a bump test on transducers, which is really testing the cone and the suspension and any other excursion parts to make sure that they can withstand long-term high excursion. We really just try and beat them to death.
So push it in and out as fast and as hard as you can, as many times as possible, and see what happens, really.
And then and on a full system like this large loudspeaker you can see down here, we'll then finally run a music abuse test, and that's playing high-level music for up to 1,000 hours.
Oh man!
So this is pushing everything right to the limits, to the highest level that the user will ever be able to put into the loudspeaker, and every single one has to last at least 1,000 hours. And we reckon that if it can do that for 1,000 hours, it should be able to stand out there in the field 5 years, 10 years, whatever it takes, and it'll survive.